Um, so if you guys remember, typically 35 current to 40% of any electrical system is actually a cooling, heating, or ventilation system in any commercial industrial building. So this chapter talks about air conditioning, which is in our case, it will be the chiller. Remember when we talked about chillers, guys, when we walked in Boston Scientific? And we'll talk about ventilation. You guys have exhaust fans, 5 exhaust fans, Adam, that you will be laying out on the commercial industrial building that we have. You are to circuit these exhaust fans. Today we're going to talk a few things about the exhaust fans. What do they do for a living? Typically, they are mechanical equipment. All what we do, guys, is provide a feeder for them. Okay? So, ventilation using exhaust fans and air conditioning, which is basically cooling the building. Cooling the building. So that's our topic for the day. Um, so let me highlight a few things, guys. So the second thing we're going to do is there's also ventilation circuit. You can talk about ventilation in an industrial plant, Karen. There's a lot of fumes and odors that you need to get rid of. So ventilation become a big deal, exhausting all these fumes outside as well as treating it. So talk about this one. Determine the required heating control. A little bit about heating. Electrical need for air conditioning. That's probably the second thing is how do you find the component for a chiller? You guys have a chiller with me. You're going to be sizing it. You're going to be dropping circuits. You will be on the schedule putting a circuit breaker and a conductor for it. How do you find a conductor and an overcurrent protection device for a chiller? We have done this before. It's not new. You, Adam, you heard about last in the commercial project. We talked about maximum overcurrent protection device and minimum circuit ampacity. Same thing. So we're going to repeat the same thing one more time for the industrial. Okay, so every building that we walk in, guys, you will have some type of ventilation. The building that we have right here has ventilation systems in it, as well as the building that we have in our project. 5 exhaust fans for ventilation. Typically, and exhausting the fumes. These guys are, this is just a little bit about how they are. You look at them, steel housing designed for mounting on a flat surface. Blower unit enclosed in the steel housing. So big fan sits, it looks like a mushroom sits right on the top of the roof in order to ventilate the space. That's what you're looking. So how do they design what size fan they put? That's none of our business, basically. That's a mechanical engineer's business, Adam. What our business is to coordinate with our fellow mechanical engineers and tell them where do you guys want, where are your exhaust fans? They put them in certain location, give us the horsepower and the voltage, and we go size the feeder that goes to it. There's a couple of vibration absorption, and all these are done by the mechanical guys. It comes as a set, guys. They sit it. The mechanical contractor will sit on a roof. The electrical contractor come and put the electrical feeder into it. Almost noiseless, obviously. You don't want to have a lot of noise during operation. It's like air conditioning. If you guys have seen the new air conditioning, they really you rarely can hear them when they're running. So they make them really good. Anyway, here's how it looks like. This is your exhaust blower. The single most important thing for us, what do they do for a living, guys? They take the air and exhaust it outside the building when needed, when called upon. Okay. The single most important thing, Adam, is one little thing right here. Can you guys see that from an electrical point of view? We have, here's where I have my disconnect, and then where it goes to the fan. So that's basically the single most important thing. There is a disconnect provided with the equipment. Manufacturer provided disconnect right by the equipment. So Adam, my job and yours is to take this and give it a circuit breaker, overcurrent protection device, as well as we need to provide a feeder to feeder. This one, guys, is typically 2.5 times full load current, and which you guys did that. And this feeder is 1.25 times full load current. Done. That's how we size the feeder and overcurrent protection device. The motor, you guys have, I tested you for that one on the motors. So that's as far as you're concerned. You need to coordinate with the mechanical engineers where they are located and how to poke right through the ceiling in order to, the roof in order to reach it. Can you guys see that? That's where you put your conduit in here and bring it into the system. Any comments, guys, about the exhaust fan? So we need to power these exhaust fans. It looks like this, guys. It takes the air. You take air comes in and then it goes all the way, exhausted outside. There's a shutter here that you can shut it. Internal wiring, disconnect. This is very important for us. And again, one more time, we interface with them right here. We take a circuit atom from our mechanical equipment to this exhaust fan. Can I guys get you to understand in the project that we have, the industrial commercial project, we have 5 fans, 5 exhaust fans that you have to circuit. They're located on the roof. 4 of them on the top roof and 1 on the lower roof. They look exactly like these. Any comments about ventilation? Their motors, their fans, we size them based on 2.5 for the overcurrent protection device, and the conductor is 1.25. Make sure you have a disconnect. Typically, they come with a disconnect, and they also, a lot of them guys have a circuit, a receptacle, so you can work on these equipments. Any comments about the exhaust fans? We don't size them, we don't specify them as equipment. All what we do is we size the feeder that comes to them. We don't lay them out. Typically, they're laid out, almost they're laid out by the mechanical engineers. Okay, for the project that we have, guys, remember we have 2 projects, Karen. We have this project that we're dealing with, and the project that you guys are working on. This is how all these exhaust fans are located right in here on the roof for this industrial building, and they're powered from right in here. And we have a controller. Each one of them have a controller, a magnetic starter. Push button, a couple of lights to give you green running, red not running. So you can push any of these buttons and turn any of these exhaust fans on and off. And they're all powered with a fuse disconnect, guys, right, coming out of this. So can I get you attention, guys? 1, 2, 3, 4, 6 blowers with 6 disconnects coming from the panel through a gutter. That's how they typically power these exhaust fans. Any comments, guys? Any questions? So, Karen, anyone can go there and push any of these buttons and start any of these fans. Does it make sense? Yes? No? Karen, are we good? Okay, so these are the 6 exhaust fans. Our project, Adam, have how many? 5. You guys are going to do the same thing. All these are going to have a start. This is your controller, and this is your overcurrent protection device. Typically, it's going to be a fuse disconnect, and you're coming from, for example, from here to the controller and out here, and an overload in it. Overload right here and going all the way to the exhaust fans. So that's my exhaust fan blowers. Moving into, guys, the terminology. So that's your exhaust fans. Exhaust fans, guys, are easy because they are they're motors. Exhaust fans are motors. Chillers. When it comes to chillers, guys, any electrical, any mechanical equipment that has a compressor in it. The NEC code book treat separately, differently, like we talked before, and they put them in an Article 414 instead of Article 430. Why? Because these guys are special. They have the compressor, the refrigerant of the compressor help cool all the pumps and the motors inside this big machine. So they can make them work harder than if they were just a fan. Can I get you guys to understand why they separate them? If you have a compressor, they call them hermetically sealed equipment. They make them work harder, so they have a special arrangement for them. Okay, there is a few things that you have to know about this. Typically for the chillers, we're talking about chillers here. Chillers, maximum continuous current. That's the highest amount of current that the equipment can work at before it fails. The manufacturer, guys, will decide the maximum continuous current. And we'll talk about this one. The other one is called rated current, load current, brand circuit selection current, minimum circuit amplicity, and maximum overcurrent protection device. We're going to go over them in a little bit more details in a second. These are the terminology related to any compressor, any equipment that has a compressor. And what's in it for you in a second here. Here's how they determine the maximum current, guys. The manufacturer of the equipment will determine it, of course. It's of the hermetically sealed motor compressor. Can you guys see the word that they use, hermetically sealed refrigerant motor compressor? You have to have a hermetically refrigerant motor compressor. It's sealed. So the way they do it, guys, you're going to see, they use the coolant mat to cool the compressor and the motor of the compressor. That's it. So if you cool the equipment, you can abuse them. You can make them work harder. So determined by the manufacturer. needed to properly design the unit. That's what the manufacturer gives it to you. Electricians need not know about it. You guys don't have to know anything about this. This is just related to them, okay? And knows this information. No, not on the nameplate. It's not on the nameplate. So they use it. Typically, guys, this is the highest amount of current that the equipment can run at without burning. So they use it for sizing. So that's a maximum overcurrent protection device. Just FYI, we don't use it for any sizing. Then you get into the rated. Now you're going to see, guys, why we use it. Maximum continuous current. Here's my maximum continuous current, right? MCC, maximum continuous current. Then they go to something called rated load current. This is so important. That's how we size things based on that. So again, determined by the manufacturer for the hermetically sealed, hermetic refrigerant water cooling. By test, they get it by testing them under the temperature condition and voltage at the right voltage. So that's a full load current of the equipment. Okay, and Karen, the number that they come up with is 64% of the maximum continuous current. So rated load current equal 64.1% of maximum continuous current. Do you guys see why they use the? Good morning, Derek. Why they use the maximum continuous current? They get the maximum continuous current and they say, you know what, we're going to rate the equipment at 64% for safety. So that's how they come up with something called rated load current. Very important because that's how we size the equipment. So, Adam, what you do then, you take 1.25 and multiply it by rated load current, and that will be your conductors. Conductors. You're going to see in a second. This is very important. Rated load current. The next one is called branch circuit selection current. Branch circuit selection current, guys, is exactly like rated load current. They define it defined by the name on the nameplate of the hermetically refrigerant designed to operate continuously at a current greater than 156 of the rated current. So what they do, at least 64 maximum overcurrent protection device. The branch, they call it branch circuit selection current, is typically, guys, equal to rated load current. Typically equal to rated load current. So Matt, what they do, because these chillers have a lot of little equipments here and there, so they take the rated load current, they add the other equipment to it, and they call it branch circuit selection current. What's in it for you guys? And it's, look at that, it's the same thing. Branch circuit selection current equal 64.1% of maximum continuous current. The same like the rated load current. So what's in it for you guys? Here's what we typically do. We use either the branch circuit selection current or the rated load current, whichever is larger, to size the fuses and the circuit breakers. Whichever is larger to size the fuses and circuit breakers. Okay. There's something called maximum continuous ampacity. Maximum continuous ampacity, MCA. Maximum continuous ampacity. This is on the nameplate. The minimum ampacity of the conductor information, very important for us, very important for designers. It determines, this is how they come up with this value, guys. 1.25 times rated load current or branch circuit selection current, whichever is larger. This is what minimum circuit ampacity is. The good news is, it's always on the nameplate. Always on the nameplate. So you don't have to even do this. So you see minimum circuit ampacity equals 50 amp, and Adam, you go 310.15 B16 and size it. No calculation needed. Can I get you guys to understand minimum circuit ampacity for chillers? We don't do any calculation. But if we are to do the calculation, that's how they do it. Now, of course, after they add also the other loads, if there's other relays and what's not in the machine, they add them after. They multiply 1.25 by rated load current. This is very important, guys. Can I get you to this is the second time we touched on that one. Minimum circuit ampacity. Whenever you have a chiller, you're going to ask your mechanical engineers, give me the minimum circuit ampacity so I can size my conductor. If it's 50 amps, no multiplication by 1.25. You just go to the table and size your conductor. Straightforward. There's something called maximum overcurrent protection device guide. Maximum overcurrent protection device. maximum overcapacity device. The same thing, the manufacturer always put it on the nameplate, always. It's determined by 2.25 multiplied by rated load current or branch circuit selection current, whichever is larger. So if you are to do the calculation, that's how they do it, how you do it. The manufacturer guys, they do it for you. So they tell you maximum overcapacity device is 125 amp fuse. So when they say 125 amp fuse, Adam, no need for you to do anything. Just go find yourself 125 amp fuse. Any comments, gentlemen? Any questions? I want you guys to understand fully these. These are very, 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 very important. Right here. Maximum overcapacity device, minimum circuit capacity, right on the nameplate. Right on the nameplate. If you don't have them, you multiply them by 2.25, or the ones that you guys did with me, the code says 1.75. If it doesn't start, you go to 2.25. The manufacturer used the 2.25. They size them, they put them in the nameplate, done. You don't have to do anything. Okay, so that's basically the equipment, guys. Cooling equipment, we talked about the refrigeration cycle. They compress the refrigerant, guys, and the chillers. You saw the chillers. They compress it, and they circulate it between the compressor, the evaporator, compressor, and condenser. And they pick the air, the heat from the building, and they exhaust the heat through the air handling unit outside. And that's what I'm gonna get you one presentation, guys, about these as we move on too. I'll get you one mechanical. I have a nice presentation about how they interface, but that's a coil that they use. If you're to use overloads, you guys have done this overload sizing for me. The manufacturer, you're very familiar with this one. Service factor, you guys remember the term service factor? You did it with your friends, 150 or more, 125. If the temperature rise is not over 40, your multiplier is 125. All other cases, your multiplier is 150. You were tested on this, if you guys recall. That's how you size the overload protection for a chiller or a motor or anything else. Exactly like we did it in our test. But you multiply Adam by the nameplate, not the NEC code book value. You multiply by full load amps for the motor. Nameplate. Nameplate value. Nameplate value. So that's basically what we do with that. Cooling unit, this is just alignment and what's not. Then we'll get into a few mechanical things, guys. Some of these are belt-driven machines. They drive the machine with a belt, so you have to have deflection on the machine and the belts and what's not. Moving all the way to the liquid chillers, I will get you guys a couple of cut sheets about a major project with liquid chillers. For major project, Adam, they don't use air conditioning, they use chillers. Now the chillers, instead of chilling refrigerant, they chill water. They just refrigerate their two cycles. One cycle, the refrigerant will chill the water, circulate the water to the air handling unit. They blow the air right through a coil that has cold water, and then from the other end you get cold air. That's what the chillers. So the job of the chiller is to chill the water, make the temperature of the water lower. So that's your job of your chiller. Okay, so hermetically motors. They call them hermetically sealed motors. Part of the refrigeration system, you're going to see in a second. So what they do is, then that refrigerant medium, that material, passes all through the motor and cool it. So if they put the refrigerant, Derek, over the motor when it's running, every time you cool a motor, you can abuse it more, right? Because enemy number one of electricity is heat. If you can cool it, not a big deal. Okay, so this chiller has two hermetically motors driving it. Each chiller unit are connected so that they cannot start at the same time. So they can't start at the same time because of air rush. So we have a chiller with two motors on it, driving it. You guys remember when we went to Allianz and have these compressors running and right by the chillers, and the chillers pump are running and what's not? These I have two of them. And they don't start at the same time because of the air rush. Here's how it looks like. You guys you've seen that when we went there. So your controller will be right in here. So when you size this one, Anna, you need two things. You need minimum circuit capacity, maximum overcurrent protection device. These two values, this one say will be 23.5 amps, say this one will be 30 amps. You go size your conductor, this will be conductor, this will be fuse or circuit breaker. Done. So that's your liquid chiller. The reason why they abuse them, I don't know if you guys can see, they take the low pressure gas and they pass it right over the rotor of the machine. And by passing it over the rotor, it cools it as it goes out. So they design it in a way that the motor is cooled by the refrigerant. So who cares? You can abuse it more. It can work harder. You can give it. That's why the code treated different than any other motor. The motors that drive the chiller, guys, they're treated differently than other motors because they're cooled. A fan up there is not cooled, is it? It just there's no coolant in it. They use a refrigerant to cool the motor as part of the process of cooling the building. And I have a presentation, guys, about cooling in a commercial building. We'll go over that one. Okay, so that's basically it. The only thing you really need to know is minimum circuit and basically maximum overcurrent protection device for motors. You guys have done calculation with me before too for this. There's something called precipitation unit. Precipitation unit, guys, to clean the air right by the machines. Remember, we have machines we're cutting, making drilling holes in aluminum and steel. So install directly behind or above or at the side of a machine. So now you're digging. Do you guys see that little machine sucking all the fumes that's coming out of it? You see them in the manufacturing all the time. So that's what they're talking about. What does it do? It takes the air right around when you're cutting, removes the mist out of it, and the oil mist, smoke, odor, and take all this one, separate the oil, put it in a container, take the odor, treat the odor, or throw it into the Mother Earth. So basically, because if you're cutting all day, guys, and you're breathing all these fumes, you're going to have cancer. So OSHA and everybody else require to have something called precipitation right next to the machine. It sucks all this, clean the air for people who are around these machines. They can salvage the oil so they don't kill the environment. To salvage it and reuse it later on in a reservoir. So it takes the oil mist, separate the oil mist, the odor and the smoke, it exhausts it outside. Does that make sense? You guys have seen them when right next to the machine and sucks the air. So that's what they're talking about, this one. What does it do for living? There's something called ionizer. How do they do? Ionizer, which is nothing other than tungsten wire. And then there's a collector cell, which is flat metal plates. You're going to see in a second. What they do, guys, is they have a high voltage transformer. They bridge the voltage into DC. And then from AC to DC, because they use DC, and they have a couple of filter capacitor to filter the DC and a blower to blow the air right through it so they can collect it. Look at how it looks like. Very simple. What they do, guys, is they bring, here's my DC. Can you guys see? Here's my ionizer. So what they bring a big transformer here, and then they have a bridge that take it from AC to DC. Okay, and here's how will you power it. All this is one big system. Now you're putting positive here. You're putting the positive sides, and they have a big fan that blows the air. They have a big fan that blows the air through a coil that's positively charged. What do you think the air is going to be? Positively charged. The particles, the mist, and all this stuff get charged. When it gets charged positively, then it goes through all these plates here, or collectors. It passes right through them with positive. So, and this is negatively charged. There's a negative here. So what happens if you have a positive mist and a negative collector or cell? The filter, it's going to attach to the filter. So they charge the dirt, guys, as it comes out, charge it positively, pass it through a bunch of filters that negatively charge, and they attract to it, electrically attract to it. That's how they collect them. Then they change these filters. Anyway, so that's the concept of operation. Of course, they use DC, so they have a high voltage transformer, bridge it down into DC. So you get your 120 volt. I don't know, you get it whatever volt you want, and you drop it down to, I don't know, let's just say 24 volt DC. And that's how you get your positive and negative. Any comments, guys? The ionizer will be positive, the collector will be negative. You take the mist, positively charge it, you blow the air, push it through the collector, it gets attached to positive, attract negative, right? It attracts the negative and you collect the dust. That's how they do this system. There's portable ones, there's fixed ones and portable ones, guys. The portable ones have flexible hose, can be positioned wherever you want them. They run at 120. They do the same principle, consume very little energy. Ionizer and collector plates are insulated from each other, like you, and current draws very little, dries very little. So they don't consume a lot of energy. They're just pulling the air and cleaning it, air cleaning. They're called precipitator. So if you hear the word precipitator, that's what they're talking about, precipitator. Some type of an exhausting system. Any comments, guys? Any questions? Comments, questions about this chapter? I do have a presentation, like I said, about chiller, air handling units, and all this together. I'll do it in a different time. So that's what we have, guys, here. Let me see if we have... We talked about the exhaust fan. Here's my exhaust fan. We talked about how you wire the exhaust fans, chillers, how to situate them, mount them, and what's not, how they work. The low pressure, can you see the low pressure comes in here, cool the rotor on the motor, and continues in its way to high pressure gas to the compressor. Continues to be to the compressor to be compressed. So here's a collector, the bridge, and that's how it looks like the precipitator. This is a precipitator, guys. We put the hose here and sucks all the fumes and clean it for you. So value, this is just a few settings for the value of the belt, not important to us. Any comments, guys? Any questions about this chapter? To summarize, guys, this is about chillers and exhaust fans. Exhaust fans are motors, easy, electrically speaking. We need an overcurrent protection device and a conductor to them. Chillers, same thing, very easy. We need an overcurrent protection device and a conductor to feed them. The controller, guys, typically the controller, as well as the overload, as well as the disconnect, is provided by the manufacturer for these. Unless they tell you otherwise, they're provided. I don't know if you can see Adam right in here. Do you see that disconnect here? Right in this area. Here's your disconnect. So all what you have to provide is come over here, overcurrent protection device, and you're done. From a panel, you're done. Okay, that's all I have for you. I wanted to do another chapter today, but we do have field trip, Derek. I forgot to tell you guys. Ouch. Did you remember that? The email now, yeah. So I would like, guys, in 5 minutes to get you with your friend Chad to go to EMI, tour EMI. It's a great tour, guys. You get yourself to... Here's what you're going to see when you go there. You're going to see a big switchgear open, and you can stick your hand and look at all this copper and aluminum that they put inside it. That's kind of the unique thing about this. They make switchgears and panels. So when you go there, unlike Allianz, where you can't touch anything, this is a lot of open spaces. You can see and touch and feel. That's really get you an idea what's inside these big panels if you've never seen it. Cool? Once you guys get yourself in 5 minutes, we have to be there at 9. I like to be a little bit earlier. I would like to leave by no later than maybe 8:15. I'll drive all of us. 8:15, shall we? Thank you. And